So I welcome you all to this lecture series on Internet of Things. We will start with Introduction to Internet of Things. So let us try to learn what is actually this Internet of Things. So it is basically a network of devices. Devices here means things. It is a network of things. Now when we talk about things, it can be anything like a small clock in your home, a umbrella, or a shoe that you wear, a simple light, or any home appliance can be a thing, and it can be connected to the internet. Not only it can be connected to the internet, we can take advantage of some technologies like big data, data analytics, machine learning to make these things intelligent, and that is what Internet of Things actually means. So if we go more formally, IoT basically comprises of, or in the Internet of Things basically comprises of things that have unique identity and should be easily identifiable from anywhere in the world and are connected to the internet. So it is also expected that by 2025 there will be a total of around 41.6 billion devices or things that will be connected to the internet. Now IoT is not just limited to connecting these things to internet, but also it allows things to communicate and exchange data so that we can take advantage of the data analytics and the machine learning techniques to make it smarter. So this is just a way, this diagram is a way in which the IoT system works. So as we can see here, there is data or the raw or unprocessed data from the IoT devices or sensors, from which we will be deriving some meaningful information by filtering, processing, categorizing, and sometimes contextualizing the data. Once the data has been gathered and the information has been extracted, then we can run some algorithms to infer some information or some understanding from the data. That is what knowledge means. So inferred from information by organizing and structuring the data. So this is how the IoT system actually operates. So these things from which we will be collecting the data can be a simple car, a smartphone, or any other home appliances, or a wearable gadget. These are all such sources of data from which we will be gathering the data, from which we will be extracting the information, and then some knowledge will be inferred from it. So some of the existing devices like the computers, 4G enabled mobile phones, they have some form of unique identities, and they are also actually connected to the internet. However, in the Internet of Things, okay, we are more interested in connecting devices. We are interested in configuring, controlling, and networking the devices or things that are traditionally not connected to the internet. So this small phrase actually summarizes about the details about Internet of Things. So some of these things can include like thermostats, utility meters. It can be a Bluetooth connected headset, irrigation pumps, sensors, control circuits. All these kind of things can be connected to the internet, and that is what is Internet of Things. So if we go by a formal definition, it can be called as a dynamic global network infrastructure with self-configuring capabilities based on standard and interoperable communication protocols where physical things have identities, physical attributes, virtual personalities, and use intelligent interfaces and are seamlessly integrated into the information network. Often communicate data associated with users and their environment. There are few characteristics of Internet of Things also. We can look into it. So these are some of the major characteristics of Internet of Things. The first major characteristic of Internet of Things is it should be dynamic and self-adapting. That means IoT devices and systems may have the capability to dynamically adapt to the changing context, take action based on their operating conditions, user context, and sensed environment. For example, let's say we have a surveillance system, let's say a home surveillance system. So let's say it will be recording the uh, like the scene of a particular room, and once it actually detects that there is some intruder inside, then it can change itself according to that context. For instance, let's say it is recording at a lower resolution when nobody is there in the room, and once it detects an intruder is present, it will be recording with a higher resolution. So that is the thing. According to the changing context and condition, it should be able to adapt. So that's why it should be dynamic. Another important characteristic is self-configuring. So it should allow a large number of devices to work together to provide certain functionality. So, for example, if we consider the case of a forest fire detection system, so we should have certain sensors that if we just put inside the forest at different locations, it should be able to configure itself. It should be able to configure its network, and it should be able to configure itself, and multiple number of devices should work uh, with cooperation to achieve their goal. Then interoperable communication protocols is another characteristic. So normally when we talk about IoT devices, it should support a number of interoperable communication protocols and should communicate with other devices and infrastructure. So interoperability is a major issue. So the different devices or things that we are talking about in IoT can be from different manufacturers and maybe based on different protocols. So the IoT system should be interoperable in terms of communication protocol. Then another major characteristic is the unique identity. So each IoT device should have unique identity, like its IP address or a MAC address, by which it should be uniquely identifiable over the internet. And final characteristic is the integrated into the information network. That means if the device is integrated into the information network, then it allows them to communicate and exchange data with other devices and systems. So it should be really easy to integrate any device into the communication network or the information network. Plug and play kind of capability should be there. So now let us look into some of the applications of Internet of Things. So some of the major applications of Internet of Things are in these sectors like home, cities, environment, energy, retail, logistics, agriculture, industry, health and lifestyle. Now that we have learned about the Internet of Things, let us now discuss the physical design of Internet of Things, like how a physical IoT device actually looks like. Now, like I told you before, that in IoT we have things which are actually the IoT devices which will be connected to internet. So the things in IoT usually refers to IoT devices which have unique identities and can perform like sensing, actuation, and monitoring capabilities. The IoT devices can exchange data with other connected devices and applications and directly or indirectly collect data from the other devices. It should be able to process the device itself, or it should be able to send the data to cloud where it will be processed. So these are some of the capabilities that the IoT device should have. So accordingly, we need all these facilities in the device or in the cloud. So when we talk about an IoT device, it may consist of several interfaces and connections to other devices. It can be wired interface or it can be wireless. But as I told, the aims remain the same. Like it has to capture some data using the sensors, then it has processed some data. It can be either locally or on the cloud. These include the IoT interfaces for sensors. Similarly, for internet connectivity also we need some interfaces. It can be a LAN interface or a IEEE 802.11 Wi-Fi interface. Then again, memory and storage interfaces, audio and video interfaces are also required in some IoT devices. So an IoT device can collect various types of data from onboard or attached sensors, such as there can be temperature sensors, humidity, light intensity, then whether any motion is there in a room or not. All these kinds of things can be easily detected using a IoT device. So this is the hardware layout, or we can call as a generic hardware layout of any IoT device. So these are the different blocks. There's a connectivity block where we have the different interfaces available for communication. So the USB host is there for serial communication, while RJ45 or Ethernet is available for internet, connecting to internet. Similarly, the processor is available for local processing as well as running the different resources. Then the audio and video interfaces are there, like the HDMI, which is a video interface as well as audio interface. Then we have a 3.5 audio jack, which is again a audio interface. The RCA video connector is also available. Besides this, the IO interfaces like the UART, that means the universal asynchronous receiver transmitter, the serial peripheral interface, and the I2C or inter-IC communication interface is also available. Besides this, the memory interfaces where you can use NAND NOR or the DDR1 to DDR3 RAMs are also available. Then graphics or GPU capabilities are available. Then for non-volatile storage, we have the SD card as well as the MMC or SDIO interface are available. Some of the devices which have all these capabilities are called single board computers, and one of those devices is this Raspberry Pi. This particular example is a Raspberry Pi 3 Model B, where you can see some 40-pin GPIO connector is available to add different sensors and actuators with this device. Then as you can see, there is a quad-core chip for processing the data. Then Bluetooth and Wi-Fi are also available on board. So these are the communication interfaces. Besides that, this LAN port is another communication interface, and the USB ports are the other interfaces. For video and audio, we have a 4-pole audio jack that is available. We have a camera port available. Then we have full-size HDMI support available in this. So like we discussed, the IoT devices can in fact exchange data with other connected devices and applications. That is one of their objectives. Then they can collect data from other devices and process the data locally, or they can send data to centralized servers or cloud-based application backends for processing the data. They can also perform some tasks locally and other tasks with IoT infrastructure based on temporal and space constraints. Now let us have a look into the IoT protocols. The protocols are the rules and regulations that govern the data transfer. Without protocols, in fact, there will be a lot of collisions and the data communication will be impossible in fact. So as IoT devices have very few little number of sensors and components, they have very smaller capacity batteries available. So there are tough design constraints actually for these protocols. So another fact is that we need to perform everything wirelessly. This communication have to be wirelessly. So the IoT protocols should satisfy these requirements. That means they should allow communication among various devices simultaneously. And normally Internet of Things is being used in critical areas like the health, home surveillance, the industries, etc. So the communication security has to be ensured. Then data should be transported efficiently. Then IoT devices can be added or removed from the IoT network easily. The IoT protocol should support the scalability. So these are some of the requirements. So if we look into the different layers of Internet of Things, these are the different protocols layer wise. If we look into the application layer, we have the protocols like HTTP, COAP, WebSockets, MQTT, all these protocols available. Similarly, for transport layer, we have TCP and UDP. In network layer, we can have IPv4, v6, or the low power wireless personal area network, which is a version of IPv6 only. Then we have the IEEE 802.3 Ethernet. We have the Wi-Fi available. We have the WiMAX available. Then the IEEE 802.15.4. So different standards are available along with the cellular standards like 2G, 3G, LTE, etc. So let us now look into the different layers of Internet of Things network and the different protocols. So first is the link layer. The link layer protocols determine how data is actually physically sent over the network. Like it's just like the physical layer, okay, or the medium. So some of the examples are like copper wire, electrical cable. These are the common mediums that are used. The scope of the link layer is the last local network connection to which the host is attached. So we will begin with the IEEE 802.3 or the Ethernet protocol. So it is basically a collection of wired Ethernet standards for the link layer. For 802.3, the kind of medium that is used is the coaxial cable. These are similar to the ones that are used by the cable operator. Then 802.3i is there. It uses the copper twisted pairs. Okay. Similarly, we have the 802.3j, which uses fiber optic connection. Then 802.3ae uses Ethernet over fiber. Similarly, other iterations are also available. So these standards provide us the data rates from 10 Mbps to around 40 Gbps and higher. It actually depends on the medium and the kind of transceivers that have been used. So this is a simple diagram which shows the Ethernet hub to which different devices are connected. So this is a Ethernet network or a 802.3 base network. The next protocol is the 802.11 or the Wi-Fi. It is basically a collection of wireless LAN communication standards, including an extensive description of the link layer. It normally operates in the 5 GHz bands if it is IEEE 802.11a. Similarly, if it is IEEE 802.11b or G, it operates in the 2.4 GHz band. Similarly, the 802.11n operates in the 2.4 or 5 GHz bands. Similarly, there is another iteration of it, which is the 802.11 AC, which operates in the 5 GHz band. The 802.11 AD operates in the 60 GHz band. So these protocols actually work to provide us data rates in the 1 Mbps to around 6.75 Gbps range. So different standards are again available. If you go to different countries, again different protocols are available for this Wi-Fi, or different standards are available for this Wi-Fi. For instance, if you go to Japan, you will find a IEEE 802.11y. It is because again different frequency bands are available in different countries, so a little bit different standards you will find with different channel numbers. Here is a comparison between the 2.4 and the 5 GHz band. As the bandwidth is lower in the 2.4 GHz band, that's why you will find lower number of channels and slower data transmission rates. Then again, there is a list of different channels in the 2.4 GHz band, as we can see, and where it is actually used. So next is the WiMAX or LRWPAN. So this 802.16 WiMAX is basically a collection of wireless broadband standards, including an exclusive description of the link layer. The WiMAX provides data rates from 1.5 MB per second to around 1 GB per second. Then there is another standard which is called the 802.15.4. Okay, it's called the LRWPAN, and it is a collection of standards for low rate wireless personal area network, and it is also the basis of some of the protocols like the ZigBee. Normally low data rate is available in the 40 kilobits per second to around 250 kilobits per second, and these standards provide low cost and low speed communication for power constrained devices. In power constrained devices, you cannot afford data rates in the 1.5 Mbps or Gbps range. Normally you will have to work with lower data rates to conserve more power. Besides this, there is this cellular network, 2G, 3G, 4G. So then nowadays you can also find 5G is also available. So these data rates can range from some 9.6 kbps to around gbps for 5G communication. So these are the different generation of the mobile communication. So if you want your IoT device to have a longer range kind of protocol, you have to use. So if you want a local coverage, then the local area network is quite like useful. But if you want a global coverage, then maybe these mobile communication networks can solve the purpose. The next layer is the network or the internet layer, and it is responsible for sending of the IP datagrams from the source network to the destination network. This layer performs the host addressing and the packet routing. Normally, the datagrams contain a source and a destination address to which the route is then decided, and accordingly, the packet actually or the datagram actually travels from the source to destination. This is again across multiple networks. So there is an addressing scheme here that is again based on the kind of protocol you are using. It can be based on IPv4 and or the IPv6. So this IPv4 is the Internet Protocol version 4. Okay, and it is the most deployed Internet protocol that you can find, and it uses the 32-bit addresses, which means there are only 2 to the power 32 addresses. So as the number of devices increased in 2011, these all addresses were actually exhausted. Now it has been succeeded by the IPv6. So this IPv6 is again another newer internet protocol which uses 128-bit addresses, which means 2 to the power 128 addresses are possible. So there is again another variant of this IPv6, which is 6LoWPAN, which is the IPv6 over the low power wireless area networks. So this is actually applicable for low power resource constrained devices, and it can operate in the 2.4 gigahertz band and provide us the data rate of around 50 kbps. Next is the transport layer. The transport layer protocols provide the end-to-end message transfer capability independent of the underlying network. So if you want process to process delivery of the packets, then this layer is responsible for it. So the communication again can be with or without the handshake acknowledgements, and the major responsibilities of the transport layer includes error control, segmentation, flow control, congestion control. These are all its responsibilities. It can control error by sending the acknowledgements. If let's say a packet is sent from the sender to the receiver and the receiver doesn't send any acknowledgement, it is assumed that the packet has not reached. So retransmission is done. That way it controls the error. Similarly, segmentation means it divides the data to be sent into small packets. So flow control and congestion control are also implemented in the transport layer. So now let us look into some of the protocols that are related to this transport layer. The first and the most widely used protocol is again this TCP, or the transmission control protocol, and this is basically the protocol that is used by the web browsers along with the HTTP and the HTTPS application layer protocols. So besides this SMTP protocol, this all uses TCP. So from the application layer point of view, it might be HTTP, HTTPS or the SMTP, but on the transport layer it will be using the TCP. So it is basically connection oriented protocol and a stateful protocol. So while the IP protocol deals with sending packets, the TCP ensures reliable transmission of packets in order. Similarly, like we discussed the capabilities of transport layer, so TCP also provides the error detection capability. The flow control capability ensures that the rate at which the sender uh, sends the data is not too high nor too low for the receiver to process. Then we have the UDP. So unlike this TCP, which normally requires carrying out an initial setup procedure by sending a request to send, then some acknowledgement that allows the user to send the data, that means the permission. So UDP is basically connectionless protocol. And UDP is useful for time sensitive applications like video streaming, etc. And they have very small data units to exchange and do not want the overhead of connection setup. So UDP is a transactions oriented and stateless protocol. And another issue with it is that it does not provide guaranteed delivery, then ordering of messages and duplicate elimination. But if you want, let's say something like video streaming, then this is the protocol to go for, because it will provide you a better data rate compared to the TCP. Next is the application layer. The application layer protocols, they define how the application interfaces with the lower layer protocols to send data over the network. Normally the HTTP, SMTP, whatever we discussed in the earlier slides, they are all application layer protocols. SMTP is also a application layer protocol. This application layer protocol enable process to process connection using the ports. So some of the well-known of these protocols are like HTTP. This is the hypertext transfer protocol, and it is the application layer protocol that forms the foundations of World Wide Web. It has some commands like get, put, post, delete, head, trace, options, etc. So the protocol follows a request response model where a client normally sends a request to the server using the HTTP commands. It is again a stateless protocol, and each HTTP request is actually independent of the previous one. So HTTP is a stateless protocol, and each HTTP request is independent of the other request. And the HTTP client can be a browser or an application running on the client device. Okay, so the next protocol is the COAP, or the Constrained Application Protocol. It is an application layer protocol for machine-to-machine application, and this is meant for constrained environment with constrained devices and constrained network. And this constrained application protocol is basically a web transfer protocol, and it uses the request response model. However, the advantage is that here it runs on the top of UDP instead of the TCP, which uses a client server architecture where client communicates with the server using the connectionless datagrams. So it is designed to easily interface with the HTTP, and like HTTP, COAP supports methods like get, put, post, delete. All these things are supported. Then another protocol is the WebSocket. It's a protocol that allows full duplex communication over a single socket connection for sending messages between the client and the server. The significant advantage is that there is a full duplex communication here. So this WebSocket is again based on TCP, and it allows streams of messages to be sent back and forth between the client and the server while keeping the TCP connection open. Mostly the client can be a browser, a mobile application, or it can be an IoT device. It is extensively used in some IoT applications. So the next protocol is MQTT. MQTT stands for the Message Queue Telemetry Transport, and it is a lightweight message protocol which is based on the publish subscribe model. Now MQTT uses a client server kind of architecture, by the client such as IoT device connect to the server, also known as the MQTT broker, and publishes normally message to the topic on the server. The broker forward the message to the clients that are subscribed to a topic. So let us look into this diagram so that we can easily understand it. So these are the clients. This temperature sensor, any sensor which is present on an IoT device can be a client, and the server is this broker. Okay, so the MQTT broker has different topics. So to these topics, these sensors actually publish their data. So once they publish the data, there are subscribers, like in this case, this computer, this mobile device, these are the subscribers. These subscribers subscribe to certain topics, and accordingly they get the sensor data which are actually related to that particular topic. For example, in this case, there can be temperature data from different rooms. Let's say we have a bedroom, a dining room, a kitchen. So different rooms are there, or the temperature data collected from those different rooms will be published to this MQTT broker. Now let's say this mobile device is there, it has subscribed to a topic, that is the temperature, of the let's say kitchen. So it will be, since it has subscribed to that, it will only get that sensor data. The advantage of this kind of mechanism is that there is a isolation between the publishers and the subscribers. Okay, so it offers a uh, kind of architecture which is more fitted for this IoT application for resource constrained devices. Next is the XMPP, which is the Extensible Messaging and Presence Protocol, and it is a protocol for real-time communication for streaming the XML data between network entities. The XMPP also powers wide range of application, which includes messaging, presence, data syndication, gaming, multi-party chat, and sometimes voice and video calls also. Now, XMPP allows sending small chunks of XML data from one network entity to another in real time. And it is again based on the client server architecture. Another kind of protocol is the DDS, or the Data Distribution Service, which is a data-centric middleware standard for device-to-device, machine-to-machine communication. So it also works in the publish-subscribe model, like the one we discussed in the case of MQTT. So here the publishers, for example, some IoT devices can generate data to topics, and the subscribers can subscribe to different topics. So the good thing about, however, this DDS is that you can actually control the quality of service, and you can also configure the reliability. Then we have the AMQP, which is the Advanced Message Queuing Protocol. It is an open application layer protocol for business messaging. The AMQP supports point-to-point and publish-subscribe model routing and queuing. So in this case, however, the broker receives messages from publishers, for example, devices or applications that generate data about them over connections to consumers, publishers, and publish the message to exchange, which then distribute message copies to the queues. So this is a little bit different than the normal publish subscribe model, that it actually uses some queues. So let us now look into the logical design of IoT. So here we will be defining some functional blocks. Okay, these functional blocks provide the system with the capabilities for identification, sensing, actuation, communication, and management. So these are the different functional groups, you can say. There is a device functional group, there is a security functional group. They have their own roles and responsibilities. So the major functional groups are the IoT functional blocks, the IoT communication models, and the IoT communication APIs. The IoT communication APIs are actually part of the communication functional group. So are the IoT communication models. And the IoT functional blocks, these are actually divided into the application function group, management, device, and security function groups, respectively. So like we discussed, the IoT functional group, it comprises of a number of functional groups that provide the system the capabilities for identification, sensing, actuation, communication, and management. So we have the device function group. So an IoT system comprises of devices that provide sensing, actuation, monitoring, and control. So you have the microcontroller device or the microprocessor device that you are using, and the sensors that are part of this functional group. Then the communication functional group is there, and its job is to handle the communication. It has all the communication protocols, and it also has all the communication APIs that we will be discussing shortly. Then we have the service functional group. Services again can be of multiple types. So different kinds of services are there, like for device monitoring, device control, data publishing. So again, if you look deeper into the services can be REST based or WebSocket based again. So these are all part of the service function group. And then we have the management function group, which provides management, or which governs the different functions of the IoT system. And then we have the security function group. Its job are like authentication, authorization. If a user is let's say going to use a IoT system, the authorization has to be there, the authentication has to be there. The user should enter some ID and password, and then should get access into the IoT system. So these are the responsibilities of the security functional group. Then we have the application function group where the IoT application is there and it provides a interface to the user to access the system. The user can control and monitor the various aspects of the IoT system using this functional group or the functional block. Now let's have a look on the different communication models of Internet of Things. First one is a request response model. So this request response model, like as the name implies, is a client server interaction where normally a client is there and it sends a request to the server and the server will respond accordingly. So I'll just show you a diagram for it. So as you can see here, the client sends a request to the server like receives the request from the client and it processes the request, looks up or fetches some values, let's say, and then it prepares the response and then sends it to the client. So it can have, the server can have some resources like databases, etc. So this model is however stateless. That means every request you send is independent of each other. And however, it is quite efficient and quite independent communication method. The next communication model is the publish subscribe model, which we discussed previously. So like we discussed in the case of MQTT, which was based on publish subscribe model, that it has publishers, brokers and consumers. So the publishers are normally the source of the data and they send data to topics managed by the broker. So publishers, however, do not know about the consumer. On the other hand, consumers subscribe to specific topics managed by the broker, and whenever a broker receives the data for a particular topic, it sends the data to all the subscribed consumers. This is a very efficient model and a very scalable model. So this is a diagram. So we have these publishers, they send the data to the server, which is a broker, and there are certain topics, certain consumers are actually subscribed to these topics and accordingly the data is forwarded to. So the next communication model is the push-pull model. So the push-pull model, in which data producers push data to queues and consumers pull data from the queues. Now producers do not need to be aware of consumers. The queues here help in decoupling the message between the producers and the consumers. So here you can see the diagram of a push-pull model where we have certain publishers and then we have the consumers. But different from the other models such as the publish subscribe model that we were discussing is the absence of the brokers. So normally this kind of mechanism helps to decouple the network between the publisher and the consumer. So whenever there is a sensor data, the publisher pushes that data into the queue, and once the consumer has the resources or it is connected to the internet, it can just pull the data from the queue. It is the exclusive pair. Normally the WebSocket communication is based on this mechanism. So this exclusive pair is a bidirectional full duplex communication model that uses a persistent connection between the client and the server. So the connection needs to be established and then there's a transmission of data between the client and the server, and the bidirectional data transfer takes place in this case compared to the unidirectional in the other cases. So once the connection is set up, it remains open until the client sends a request to close the connection. So it is clear from here that it is a stateful communication model and the server is aware of the open connection. So this is the diagram of a client server strategy, and this is basically depicting the exclusive pair communication model. So as you can see, there is a request to set up connection from the client to server. In response to that, the client's request, the server actually responds through a response, okay, that actually accepts the request. Now the message transmission can take place from client to server and from the server to the client. This is actually bidirectional and this goes on parallelly. Now the connection close request can be sent by the client and then the connection close response is then sent by the server. So next we will be looking into the IoT communication APIs. So when we discuss about the different communication APIs, there are actually two broadly used APIs. One is the REST-based communication APIs. The other is WebSocket-based communication APIs. Okay, now for your information, let me just tell you what is an API. An API, or we call it the application programming interface, is a set of rules or protocols, you can say, that let software applications communicate with each other, and they can even exchange the data, features, and functionality. So here the communication API means it is related to the data exchange basically. The first one is the REST-based API, or the request response based model. Okay, so this REST actually stands for the representational state transfer, or REST in short. So in the later on in this course we will be just discussing about REST API. We will be using REST API. So there you have to understand that it is representational state transfer. Okay, so it is a set of architectural principles by which we can design web services and web APIs that focus on system resources and have resource states addressed and transferred. Now this REST is again based on like request response model, communication model that we discussed earlier. The REST architectural constraints apply to the components, connector, and data elements. So this is a basic example of a REST-based API, and this is how the communication takes place. So here you can find there is a HTTP client, which we call as REST-aware HTTP client, and it is sending some packets, and that packet in this case is a HTTP packet. So since this is a HTTP packet, it will have the different commands like get, put, post, delete, and the payload can be either in the JSON format or the XML format. So it is sent to the HTTP server for authorization. Okay, once the user is authorized, then the RESTful web service can go on. So actually the client might be trying to access some resources from the server. So server has some resources, so using which it can actually provide the data that the client actually requests. So some of the important parameters of the REST API are here. These are often called the REST architectural constraint. So first is the client and the server. So the principle behind client server constraint is the separation of concern. The separation allows the client and server to be independently developed and updated. Okay, so they have to be they can be different. So you don't have to follow the same architecture or the same programming language for the client and the server. So only thing that should be standard is the HTTP protocol that you are using. So your like server can be Windows based and your client can be again based on Linux. That is the fact. Then another thing is the being stateless. So each request from client to server must contain all the info. So actually it is a stateless protocol. Okay, the client and the server, they do not know whether the connection actually exists. So every time there is a request, the client must send all the information necessary to recognize itself, okay, and to inform the server what data it needs. It is necessary to understand the request and cannot take advantage of any stored context on the server. Now cacheable. Cache constraint actually requires that the data within a response to a request be implicitly or explicitly labeled as cacheable and non-cacheable. So if you want a data packet to be cacheable, the same should be explicitly mentioned in the label. Then only it can be cacheable. Then it follows a layered system. That means the constraints, this actually constrains the behavior of components, such as each component cannot see beyond the immediate layer with which they are interfacing. Another thing is another constraint is the user interface. So this constraint requires that method of communication between the client and the server must be uniform. So another one is the code on demand. That means servers can provide executable code or scripts for clients to execute in their context. This is basically the communication diagram of the REST-based API. So there's a request using get, put, update, or delete. These are the HTTP commands, and with the payload which is in JSON or XML format to the server. So there's a response from the server that is also in the JSON or XML format. Then there is again another request, and in response to that there is a response from the server. So this process actually goes on like this. So for those kind of systems, IoT systems, where the data transmission and reception is not continuous. That means after some instant you need to send some data and then you have to get some response. That kind of communication, uh, for that the REST API can be the best. So next is the WebSocket based communication API. Now these WebSocket APIs allow bidirectional full duplex communication as they are based on the exclusive pair model. Okay, so the WebSocket communication begins with a connection setup, like as was there in the exclusive pair communication model. So normally a connection setup has to be done between the client and the server. Okay, so this request, sometimes called the WebSocket handshake, is sent over the HTTP and the server interprets it as an upgrade request. So if the server supports WebSocket protocol, the server responds to the WebSocket handshake response, and after the connection is set, the client and the server can exchange data in the full duplex mode. Now WebSocket APIs reduce network traffic and latency. That is their advantage, because there is no overhead of connection setup in every data communication that goes on. Like in the case of REST, every request was a new request, but in this case, once you set up the connection, you don't have to send any of the redundant data for setting of the connection. Now WebSocket is suitable for IoT applications that have low latency requirement and high throughput requirements. So this is an example of the WebSocket based communication protocol, and then you can see there is a client and a server, and exactly the same exclusive pair kind of communication strategy has been implemented. So there is a connection setup request here, and then according to that the server is giving a response. This is called the initial handshake, and this happens over the HTTP. And then you see the bidirectional data communication is going on. This can happen parallelly, the transmission and reception of packets. Then there is a connection close request, and in response to that the connection is closed. So while we have already discussed a lot of the things about the Internet of Things, now is the time to understand the enabling technologies for the Internet of Things. Like what are the technologies that are responsible for enabling this IoT? Some technologies that actually work in the background and they are the core technology behind it. So some of the technologies that are actually behind Internet of Things are wireless sensor networks. This is basically a sensor of smaller nodes, okay, that can be deployed in a wide area, okay, and this kind of network have their own data collection and routing capability. And cloud computing is another important enabling technology. Then big data analytics. So the sometimes, as in the case of industrial IoT, the amount of data generated is actually quite huge. So normal data analysis techniques do not work. So you have to go for big data analytics. In that case, you have to use machine learning or similar methods to mine the data from these big data warehouses. Then embedded system is another enabling technology. Then security protocols and architectures, communication protocols, web services, mobile internet, and semantic search engine. These are the enabling technologies, out of which we will be just discussing the major technologies. So the first enabling technology that we'll be discussing is the wireless sensor network. It normally comprises of distributed devices with sensors that are used to monitor the environmental and physical conditions. Normally, if you want to detect, let's say, forest fire, etc., then you can deploy a wireless sensor network. Or let's say you want to find out the environmental conditions, like what is the temperature, or what is the humidity level, or what is the presence of, or the percentage of CO2 in a particular area in ppm, let's say, or you want to find out the presence of harmful gases in a particular large geographical area, you can deploy it. So a WSN actually consists of number of end nodes and routers and a coordinator. So end nodes have several sensors attached to them, and these end nodes can also act as routers. So like the other routers, here in this case also the routers are responsible for routing the data packets from end nodes to the coordinator. So the coordinator normally collects the data from all the nodes, and the coordinator also acts as a gateway that connects the WSN to the internet or to the cloud. one of the most important wireless technologies that is used in the wireless sensor networks is the Zigbee, and it actually operates in the 2.4 gigahertz band and can offer data rates up to 250 kbps. Okay, the range of Zigbee is around 10 to 100 meters depending on the kind of power output and environmental condition. And the power of WSNs lies in the ability to deploy a large number of low cost and low power sensing nodes. So these are again like self-organizing networks. You have to just put the nodes at different locations. They will organize themselves. They will connect among themselves. They will establish the routing paths, etc. Now, since WSNs have large number of nodes, manual configuration of each node is not possible. That's why they have the self-organizing capability, and it also makes the network robust. So in case of, let's say, failure of a few nodes, they can easily reroute data. So some of the major uses of these WSNs are in these fields, like weather monitoring system, indoor air quality monitoring systems, soil moisture monitoring systems, surveillance systems, smart grids, structural health monitoring. These are some of the major applications. So next is the cloud computing. So it is a transformative computing paradigm that involves delivering applications and services over the internet. Normally, the cloud computing involves the provisioning of computing, networking, and storage resources on demand, and providing these resources as metered services to the users in a pay-as-you-go model. Okay, so this cloud computing resources can be provisioned on demand by the users without requiring interactions with the cloud service provider. You can simply use your credit card and buy the services that you require. Okay, so the process of provisioning resources is again automated, and the cloud computing resources can be accessed over the network using standard access mechanism. So it can be computing, storage. These are some major characteristics. So resources pooling, on-demand self-service, easy maintenance, scalability and rapid elasticity, economical, measured and reporting service, security, automation, resiliency and availability, large network access are some of the major advantages of the cloud computing. Normally the cloud can be in the form of a public cloud, private cloud, hybrid cloud, but the services they offer can be in these three forms. The first one is infrastructure as a service, or IaaS, platform as a service, PaaS, and the software as a service, which is SaaS. One by one we will discuss what are these. So when we discuss about infrastructure as a service, it provides users the ability to provision computing and storage resources. Now these resources are provided to the users as virtual machine instance and virtual storage, where the users can deploy their own operating systems, their application of their choice, and the virtual resources provisioned in the cloud. Now the cloud service provider manages the underlying infrastructure only. Okay, the virtual resources provisioned by the users are built based on the pay-per-use paradigm. Okay, so similarly, there's this platform as a service, which provides users the ability to develop and deploy applications in the cloud using the development tools, APIs, software libraries, and services provided by the cloud service provider. Now, the cloud service provider manages the underlying cloud infrastructure, including the servers, network, operating system, and storage. The users are only responsible for developing, deploying, configuring, and managing the applications on the cloud infrastructure. Next one is the software as a service. Software as a service provides the user a complete software application or the user interface to the application itself. The cloud service provider manages the underlying cloud infrastructure, including servers, network, operating system. Everything is actually managed by the service provider in this case. Only even the application are provided to the user through a thin client interface like the browser. So these applications have the benefit that they are platform independent. You just need your browser to access them. Some of the services like the Adobe Photoshop cloud or the Autodesk based cloud services, these are some of the examples of this software as a service. The next important enabling technology is the big data analytics, and this big data analytics is defined as collection of data sets whose volume, velocity, or variety is so large and it is so difficult to store, manage, and process and analyze that the traditional database management tools doesn't work here. So you have to use the big data analytics to actually do it, and that actually requires use of some machine learning based algorithms to access the data or to mine out the data. Big data analytics involves several steps, starting from data cleansing, data merging, data processing, and then only you can go for visualization. Some of the examples of big data generated by IoT are like sensor data generated by IoT systems, machine sensor data, health and fitness data, data generated by IoT systems for location and tracking devices. These all require the big data analytics to be implemented. Some of the major characteristics of this big data are volume, velocity, and variety, where volume refers to the size of the data sets that need to be analyzed and processed, whereas velocity, it means actually the exponential growth of data, the velocity at which the data is generated and how frequently it varies, that is actually defines the velocity. Similarly, variety refers to the form of the data. That means big data can come in different forms, like it can be structured, semi-structured, or unstructured data. It can include text data, image data, audio or video data, or sensor data. So this is meant by variety. Another important enabling technology is the protocol, and we have already covered a lot of these communication protocols. So they are the backbone of this IoT system. So another important enabling technology is the embedded systems. So these embedded systems is a computer system that has computer hardware and software embedded to perform specific tasks. For instance, the control system that you use in your washing machines can be considered as an embedded system. So in contrast to the general purpose computers or personal computers, which can perform various type of tasks, the embedded systems are normally designed to do a specific set of tasks. So it can include microcontroller or microprocessor also, but as I told, these are designed to do specific set of tasks.